Hey everybody, welcome back to the Feynman technique. Today we'll be taking a look at an integral that I adapted from a problem off of the channel Michael Penn. Yes, Michael Penn again. The original integral was x cubed plus 1, which I've already solved. That was my previous video. That was example 81. This is example 82. In the last video, we used the tool, we used the sum of the alternating sum of the reciprocals of the squares. In this video, we will be just using the plain old sum of the reciprocals of the squares, which is equal to pi squared over 6. I will try to remember to link to my video on how you derive that. If not, if I forget to do that, there's plenty of videos on that. That's called the Basel problem. Basel problem. I'm not sure how you pronounce it. Basel, I think. All right, so let's get started. Right off the bat, I'm just going to set this equal to the integral from 0 to 1 of natural log x over x cubed minus 1 dx plus the integral from 0 to 1 of x natural log x over x cubed minus 1 dx. And that comes from a very familiar trick that I've done on this channel many times. I break this up into two separate integrals and then perform the substitution u is equal to 1 over x on the second one. Obviously, the way I break it up is one integral going from 0 to 1 and then the next one going from 1 to infinity. Watch some of my other videos if you want to see exactly what I did there. But most of you should have no problem getting from there to there. All right. Next, let's create a function of t equal to the integral from 0 to 1 of x to the t over x cubed minus 1 dx. And some of you are probably thinking to yourself, wait a second, that doesn't converge. You're right, it doesn't. Luckily, we're not actually going to be using f of t to solve this. We're going to be using its derivative. The derivative of f of t does converge. Using the Leibniz rule for differentiation under the integral sign, we can obtain f of t by taking a derivative with respect to t, the partial with respect to t of the integrand. So that's going to be equal to the integral from 0 to 1 of x to the t natural log x over x cubed minus 1 dx. All right. Now we can see if we take f prime at 0 plus f prime at 1, we get back our original integral. See, f prime evaluated at the point 0, that would just make this x to the t go away. So we'd have integral 0 to 1 of natural log x over x cubed minus 1, which is the first part. And if you evaluate it at 1, you'll recover this x. Okay. So next what we want to do is find a different way to represent our f of t. So let's see. F of t could be written like this. We could say that that's the integral from 0 to 1 of x to the t times the sum as n goes from 0 to infinity of x to the 3n. The sum as n goes from 0 to infinity of x to the 3n is equal to, there would actually be a negative. That would be the sum as n goes from 0 to infinity of x to the 3n is equal to 1 over 1 minus x cubed. So 1 over x cubed minus 1 would just be the negative of this thing. All right, and then we'd have dx. Okay, then we can bring this x to the t inside our sum because it is independent of n. And then we can use Fubini's theorem since there's no problems with convergence. To get the sum as n goes from 0 to infinity of the integral from 0 to 1 of this thing. And that will just give us 1 over 3n plus t plus 1. And of course, this also does not converge. This this sum, that's a divergent sum. That is a variation on the harmonic series, which does not converge. Luckily, like I said, we're not interested in f of t. We want f prime of t. So we can obtain f prime of t the same way we obtained it over here, just by taking a derivative with respect to t. That's what f prime of t is. So, taking a derivative with respect to t of this thing will give us the sum as n goes from 0 to infinity of, well, this would become negative 1 over 3n plus t plus 1 all squared. The negatives would cancel, so we just get 1 over 3n plus t plus 1 all squared. Okay. Now we can use this on this to obtain I. Okay. So that means that I is going to be equal to the sum as n goes from 0 to infinity of 1 over 3n plus 0 plus 1 all squared. So just 3n plus 1 all squared plus the sum as n goes from 0 to infinity of 1 over 3n plus 1 plus 1, so 3n plus 2 all squared. All right. We'll use a familiar trick on this. We will advance our n by 1, and this would become 3n minus 2. And we'll do the same thing here. We'll advance it by 1, and this would become a 3n minus 1. Okay, well, is that as far as we can go? No. If you watched my last video, you probably have a pretty good idea of what I'm going to do. We already said we're going to be using this identity right here, the sum of the reciprocals of the squares. All right. So let's rewrite our sum of reciprocals of squares like this. Let's say that pi squared over 6 is equal to, we're going to have 3 separate sums. The first sum is going to go from, well, they'll all go from 1 to infinity. And then we'll have 1 over, and I'm going to call it 3n, well, I'll write it all out. 3n all squared plus the sum as n equals 1 to infinity of 1 over 3n minus 1 all squared, 3n minus 1 all squared, plus, you know what, let me redo this. Okay, so we have pi squared over 6 being equal to the sum as n goes from 1 to infinity of 1 over 3n all squared plus sum n equals 1 to infinity of 1 over 3n minus 1 all squared plus sum as n goes from 1 to infinity of 1 over 3n minus 2 all squared. And this is equivalent to that because if you take n equals 1, you'll get the third term of this. N equals 2 will give you the sixth term of this, and the ninth, and the 12th, and the 15th. And then you'd also have this. If you took n equals 1 on there, you would recover the second, fifth, 8th, 11th, and so on. And this one would give you the first, fourth, 7th, 10th, 13th, etc. So every single term in here is contained in here. So they're equivalent. All right. We can bring out we can factor out a 1 over 9 on this first one. Okay. Well, this is exactly pi squared over 6. So we can say that pi squared over 6 minus 1/9 of pi squared over 6 is equal to this. Well, that would be 8 pi squared over 9 times 6, right? Take pi squared over 6 and subtract 1/9 of pi squared over 6. You get 8/9 of pi squared over 6, or 4 pi squared over 27. And that's equal to this, which is exactly what we have here. So this is I. So there's the answer. 4 pi squared over 27. Hope you enjoyed that.